So today we are going to look at some different ways to find enthalpy. As a reminder of what we've already done, we found enthalpy through the use of stoichiometry, and we found enthalpy of a reaction through the use of coffee cup calorimetry. Now we're going to utilize something called heat of formation in order to find enthalpy a couple more ways, a couple different ways. Heat of formation, it's super important for you to understand that it's the change in enthalpy associated with the formation of 1 mole of a substance from its free elements. So if you look at all of these equations, do you see how you're forming 1 mole of them? And you're forming them from their elements. So you have the H2 plus the O2. We have a half there because this equation has to balance with a 1 in front of the product because that is what the definition is. So fractional coefficients are going to be okay. Yeah, so notice down here in magnesium carbonate, we're forming 1 mole of it. So we need 1 mole of magnesium, 1 mole of carbon, and we need 3 oxygens, and the only way to make that balance with an O2, because oxygen as a free element exists as O2, is to do 3 halves. So each one of these heat of formation equations has a value associated with it. These are the actual heats of formation. You can find a big table of heat of formations, usually in the back of chemistry textbooks, or you'll be given heats of formation values. But what I need you to know is what that heat of formation value means. It means for every 1 mole of water that is formed from its elements, we give off negative 285.6 kilojoules. And for every 1 mole of this, we give off that much. And for every 1 mole of this made, we give off that much. So they're super important definitions that you need to know. Let's practice writing some of these heat of formation equations. We're not going to deal with any values just yet, but to form 1 mole of this substance from its elements, which is what heat of formation is, we're going to have 1 CH4 here in the products. We have to leave that as a 1. So it means we're going to add a carbon plus 2 hydrogens. All right, that one's pretty easy. So now let's go ahead and form 1 mole of calcium phosphate, Ca3PO4 2. So to do that, again, this is making things from their elements. So we have 3 calciums plus 2 P's plus 4 O2s. Now notice we're not just saying calcium plus phosphate. We're not talking about solutions. We're not talking about ions. We're talking about forming these substances from their free elements. Another thing that is good for you to know is something called enthalpy of combustion. That is a different definition, equally as important. It's the amount of the amount of heat produced when 1 mole of a substance is combusted. So instead of having 1 mole of a product in these reactions, we want 1 mole of the reactant. So here we're going to combust 1 mole of CH4. And when we do that, we add to it, let me erase that because I only wrote that down because I knew it was coming. So we're going to combust that to make CO2 and H2O. So we have to balance this, leaving that 1 there. If it leads to a fractional coefficient, so be it. But we need 1 carbon, and we have 1 carbon. We need 4 hydrogens, so we need to put a 2 there to make 4 hydrogens. That in turn leaves us with 4 oxygens, so all we need there is a 2 to balance that oxygen. And this next problem, we're going to combust C3H7OH, better known as propanol. And again, we're combusting, so we need 1 mole of that combusted, which makes CO2 and H2O. So keeping that 1 in mind, 3 C's, 3 C's, 8 H's, 7 plus 1 is 8, so we need a 4 there. And now this all leads us with 3 times 2 is 6 plus 4. We have 10 oxygens on this side. One of those oxygens is there, so that leaves us needing 9 additional ones. That's an odd number, so whenever you have an odd number, we're going to make a fraction here. 9 over 2, 9 divided by 2 times 2 oxygens is 9. So again, fractional coefficients are totally acceptable when you do enthalpies of combustion and enthalpy of formation equation writing. So now that we know what heats of combustion and heats of formation actually are, we can utilize those equations and those values to find heats of reactions. So the process that we're going to use to find the heat of the reaction here is we call it the Flippy thing. That's a Westlake term. Please don't call it that on the AP because they're not going to know what you're talking about. But I call it the Flippy thing because we're going to take these heat of formation reactions that we're being given. Notice we're forming 1 mole of a substance in both of those. We're going to take those heat of formation reactions and manipulate them, flip them, add them up, do whatever in order to find the enthalpy of this equation, which is what I call the goal equation. So we have the goal equation. What I'm going to do is go to the first reaction, and I'm going to look at it, and I'm going to compare it to the goal and go, okay, what is it the sole source of that the other equation can't give? And I'm going to see, oh, CO is in the first equation, and it's also in the goal, but I notice it's a reactant in the goal, so I'm going to rewrite that equation reversed. And when I do that, I have to change the sign because exothermic becomes endothermic, right? And then the next one, my CO2 is here, I'm just going to leave that one alone, and I'm going to rewrite the second equation. And I'm going to leave that alone, my H. So now I'm going to add these up and make sure that I actually get my goal equation. My C's cancel. I notice I have 1/2 O2 and 1 O2. If I get rid of a half of an O2 from each side, it leaves me with a half there. So my final equation should look like this. And I check, does that match my goal? Yeah, it sure does. So that means then if I add the equations, I can add the values. This is not like equilibrium, if you remember, where we multiplied the K's. Here we're just going to add the delta H's since we added the equations. Here we have another Flippy thing. This one's a little bit different because if you notice they give us our equations, right, 1, 2, and 3, but they say calculate the heat of the reaction for the combustion of 1 mole of ethane. They don't give us straight up a goal equation, so we need to write it, but they give us enough information about the goal to do that. It's basically we need to write a heat of combustion. So we're going to combust 1 mole of ethane. So we have to write that balanced. Now this is going to be a good one because we're going to get a fraction. It's kind of exciting. So if you look, we have 2 C's, so I need 2 C's. Whenever you're balancing combustion equations, I highly recommend that you balance your oxygens last. So we need 2 C's, 2 C's, 6 H's, so I need a 3 there to make 6 H's. Now if you look, I need 4 plus 3, I need 7 oxygens. So I have an O2, and I have to leave this as 1. So all I'm going to do is do 7/2 here, and that's going to be a balanced goal. So this is my new goal now. And now I can manipulate again the same way I did before. I'm just going to call this equation 1, 2, and 3, give you all a reference point. So I'm going to start with the first one like I always do. And I notice that the ethane is a product, but in equation 1, the ethane is a product, but I need it to be a reactant in the goal, so I'm going to flip that first equation and do C2H6 gives you 2C plus 3H2. So then I have to change the sign to plus 84.68. And now I look at equation 2, and equation 2 has a CO2 in the product, which is great, but if you notice in the goal, we need 2 CO2s. So I'm going to multiply that equation through by 2 and leave it exactly as it is. Now if I multiply the equation by 2, what do you think happens? You got it. I'm going to multiply the delta H by 2, and I get negative 7 288. And then my last equation, do I need it? I do, because I've got 3 waters in my product of the goal, and I only have 1 water in equation 3, so I'm going to multiply that one by 3. So I'm going to get 3H2 plus 3 halves O2 gives us 3H2O, and when I multiply that by 3, I get negative 858. Now before I total up, I need to verify. Don't be like assuming it's going to cancel out. I need you guys to write the new equation that you found and make sure it matches the goal. So my C's do cancel. My H2s should cancel. Did I forget an H2 somewhere? Oh, I have an error. You all probably saw it. This is really an H2. That would explain that. So yes, my H2s cancel. And then I'm going to have to combine some O's here. And this is cool, because math is cool. If I have a 3 halves here that I have to add to 2, I know I need to make a fraction. So 2 is the fraction with the denominator of 2 is 4 over 2. So what's 4 over 2 plus 3 over 2? Oh, 7 over 2. How conveniently perfect. So we get 7 over 2 O2s gives us 2CO2 plus 3H2O. Does that match our goal? Absolutely. So we can, yay, add that up. And that is our delta H of our reaction. Okay? All right. So now that we've done the Flippy thing, I'm going to introduce you to the Big Mama equation. The Big Mama equation is called Big Mama because we use her all the time. In class, I'll show you guys Big Mama. She's a cartoon. I'll point her out to you when you're in class. But it's always the sum of the heat of formations of the products minus the sum of the heat of formations from the reactants. You'll either be given a big table to pick from, or you'll actually just be told specifically what the heat of formations for the individual substances are. So if we look here, we're going to find the delta H for the following reaction, and all they gave us were heats of formation. So that's when we know we have to use Big Mama. We don't have a choice. So let's set her up. Big Mama is delta H is equal to, it's the sum of the products. That's what this sigma is. And each product has to be multiplied by the coefficient, because remember, heat of formation is the heat associated with 1 mole of a substance. So for instance, when we're looking at NaOH, that's 2 moles. So we're going to have to double that and do that times the heat of formation of NaOH. Now, free elements all have heats of formation of 0. So that would be plus 0. So because of hydrogen. So sum of products minus the sum of the reactants. So we have 2 times 0 for sodium plus 2 times water liquid on this table is negative 286, because I'm out of space. So it's really, really easy to make calculator errors on these. I want you to check your work multiple times. So I did this, and my answer came out to be negative 368. It is kilojoules per mole, not per mole of each individualized thing, it's per mole of reaction. So to be safe, I would just write per mole of reaction. And that is how you use Big Mama. Let's try it again in the next problem. So calculate the delta H for the following. Again, they had the reaction. They only gave us heats of formation, so we can't do the Flippy thing or anything. Well, we could, but it would be ridiculously long. I can show you that some other day. But now we're just going to use Big Mama and do products minus reactants. So delta H is equal to, I'm actually going to carry this down to here where I have more space. So delta H is equal to products 2 times CO2 is negative 393.5 plus 3 times the H2O liquid of negative 285.9. Those are my products, minus I have my ethanol at 1 times negative 278. And notice I have a free element there. It's not even in the table. So when you don't have a delta H of a free element, that's cool because it's 0. So we put that. You can put this straight in your calculator if you use your parentheses and brackets appropriately for order of operations. So delta H is equal to negative 1,367 kilojoules per mole of reaction. Okay. All right. Now let's try number 20. I like number 20. It's somewhat sexy because if you look at this problem, and we're going to actually need to use the data from up here to solve it, but it says the standard enthalpy of combustion is of C6H12 is negative 3,924. If you look, this equation is the heat of combustion. So the whole equation has a delta H of negative 3,924. Again, this says standard enthalpy of combustion of C6H6. That is the equation describing what that problem is saying. This is telling us specifically to find the heat of formation of just this individual guy. So what we're going to do, this is really cool, we're going to use Big Mama. And we're going to take all these other values that we were being given, as well as setting it equal to here, and solve for that as an X in Big Mama. Solve for it as an individual heat of formation. So we're going to have negative 3,924 is equal to products. So we have 6 times negative 393.5 plus 6 times that water of negative 285.9. So that's products minus, okay, oxygen's going to be 0, so the only thing on the reactant side is a 1x. That is what we're solving for. So our negative 3,924, I end up getting negative 4076.4 minus x. Add that negative 40764 to both sides, I get 152.4 equal to negative x. So my x then is equal to negative 152.4. And again, it's kilojoules per mole. This time it's not per mole of reaction. This is actually the heat of formation of just that cyclohexane. Okay, and our third way to find delta H for the day is using something called bond energy. Yay! I actually like this one. This one's fun. Bond energy, whenever you see bond energy, you don't think products minus reactants. You actually think bonds broken minus bonds formed. This is just an alternative version of Big Mama. But what it does for us, it takes into account the sign changes that occur. When you break a bond, you have to put energy in, so those have to be positive. When you make a bond, energy is released, so we would physically have to make bond energies negative if we were going to use Big Mama. What bonds broken minus bonds formed does, it takes that work away. So all we have to do is take energy from the table and do broken minus formed and be done with it. It's super simple. So when we have H2, we know that it looks like that, right? And when we have F2, it looks like that. And when we have two HFs, we have two things that look like that. So all we have to do is, looking at our bond energies, we're going to take the sum of the bonds broken minus the sum of the bonds formed. So HH bond, if you look at the table, is 432 kilojoules per mole. An FF bond is 154. And we have two of these guys that are formed of 565. So if we do bonds broken, 432, the sum of the bonds broken minus the sum of the bonds formed. We have 2 at 565. And that will give us our delta H. I love those. Those are so easy. They're so easy, we're only going to do one. The only trick is to make sure you count all the different bonds. Sometimes you have structures that have multiple, like you could have CCl4 or something, right? So in a place like that, you're going to have 4 C to Cl bonds that you have to take into account. They're all not going to be really necessarily super simple compounds like those. But again, just remember, if you have bond energy, you do bonds broken minus bonds formed. Okay, so we've been through all the ways to find enthalpy. We're going to wrap this lecture up with a little just recap. So remember, when we are given the delta H of a reaction and we're asked, how much heat is associated with X number of grams or X number of moles, we're going to do dimensional analysis using stoichiometry. Super simple. Calorimetry, we're going to find delta H by using Q equals MCAT. And if heat is lost to the environment, remember, we're going to add to that the Q equals cat. And we always have to change the sign if we're using a thermometer, right, to get that delta H of the reaction. We can also use Flippy thing, where we have a series of equations that we can manipulate to find the delta H of a goal. We can use Big Mama, like we learned today with products minus reactants. You're going to be given a list of heat of formations, and you can use those heat of formations to find delta H. Or like in that last example we did where we were given the heat of combustion and we found one heat of formation within the Big Mama equation. Big Mama is very, very huge. And then our final way, using bond energy, we know that if we have bond energy, we always do bonds broken minus bonds formed. And those are the ways to find delta H. Have a good day.